Hey guys, this week we're going to finish up talking about logarithms. We're going to talk about the graphs of logarithmic functions, and we're going to talk a little bit about transformations, in particular vertical and horizontal shifts. So that's going to be the very beginning of 6.1. All right, so the first thing we need to talk about is the relationship between an exponential function, so a function y equals b to the x with base b, and the function y equals log base b of x, so same base in both cases. These guys are going to be inverse functions. So I've been talking about exponentials and logarithms undoing each other, and we're going to get a little bit more, we're going to go a little bit more into depth with this today. Okay, so let me show you what this looks like pictorially, all right? So we have this exponential function y equals 2 to the x graphed here, as you can see in red. So this is just a standard exponential function that is increasing as time goes on. So as time goes on, the y values get bigger and bigger and bigger. And its inverse function is going to be y equals log base 2 of x. So this guy is going to look like this blue curve right here. So this time, so like if we talk about inputs and outputs, so if we look at this logarithm here, our output is actually the exponent. Right? Because remember we had y equals log base 2 of x, and sometimes we thought of y as c. So the way that we wrote this was 2 to the c, or 2 to the y, equals x. Okay, so our output is going to be the exponent that makes this true. All right, so let's look at a couple of ordered pairs on both of these graphs. So if we consider this guy, if we consider the points where x is equal to -1, 0, 1, and 2, we input these x values in here. So 2 to the -1 is going to give us a half, 2 to the 0 is going to give us 1, etc., etc. And we get these points. And over here with the log, it's reversed, right? The y's of the exponential become the x's of the logs, and the y's of the logs are the x's of the exponentials. So we basically just flip the x and y values. And we can see this graphically because I've plotted the points on each of the curves. So there's 4 points on each curve, and each of these points, if you were standing on one side of this green line is y equals x, it acts like a mirror for these points. So you can see that, for instance, this point is reflected across the mirror, giving us this point. This point reflected across the mirror is giving us this point, and so forth. So that's what it means pictorially when two functions are inverses of each other. The x's and the y's swap, and they make this pretty little picture of the points being mirror images across the line y equals x. Okay, so that's the idea here. So y equals b to the x and log base b of x are inverse functions. So we talked about this a little while ago, but I just want to remind you guys that with a function and its inverse, we switch the domain and range. So in our case here, the range of the exponential 2 to the x is the domain of its corresponding log function, and the domain of the exponential is the range of the corresponding log function. We also have something called a horizontal asymptote, And so the horizontal asymptote is basically the horizontal line that the function can't touch. Let me define that down here. A horizontal line that a function gets close to but doesn't necessarily touch it. Okay, so that's what a horizontal asymptote is. Exponential functions have horizontal asymptotes. So like, if we look at this picture here, so here we have our function y equals 2 to the x in red. And we can see the horizontal asymptote. It's going to be this line, this horizontal line that goes through the x-axis. In other words, the horizontal line y equals 0, right? Because this function, we can never figure out an x value such that we evaluate the function to give us y equals 0. There's no such x value, but we can get very, very close. So that's what the horizontal asymptote is. Now, on the other hand, the vertical asymptote is just the vertical line that a function gets close to but doesn't necessarily touch it. Doesn't touch it, ever. So let me write that down here. So this is our vertical asymptote, and you guys have probably heard this before in another class. So this is going to be a vertical line that a function gets close to but doesn't touch. And by the way, horizontal lines are always of the form y equals a number. And vertical asymptotes are always of the form x equals a number. Okay? So like y equals 0 was our horizontal asymptote for the exponential. And the fact that these guys are inverses says, hey, the horizontal asymptote of the exponential is going to be the vertical asymptote of the log, the same number that is. So in our case, we can see that the log function is getting very close to the vertical line x equals 0, but it's not actually touching it. So this is our vertical asymptote for the log. And this guy, remember, was our horizontal asymptote for the exponential. All right. So let's do some practice with this. So the whole idea here is that we can figure out what the inverse is because, what did I call the letters here? B to the x. I see. Okay, so we said y equals b to the x and y equals log base b of x are inverse functions. So we're given y equals 3 to the x. Well, what's our b? b is equal to 3. And so the inverse function has to be of the form y equals log of base b of x, which is 3. So the inverse function is just going to be y equals log base 3 of x. Okay, so that was our first mission here, to find the inverse function. And it says, find its domain, range, and vertical asymptote, and then sketch both the exponential and the log functions. All right, so how do we figure out what the domain is? How do we figure out what the domain and the range are? Well, the range is easy. The range is always going to be all real numbers for any basic log function, even if it's shifted up or down, the range is still going to be all real numbers. So negative infinity to positive infinity. This is always for now. All right. So the possible outputs of this value, of this function, is the range. The domain, on the other hand, the domain occurs when the argument is greater than 0. Right? Remember, we had that rule last time. We want to make sure whatever is in parentheses is bigger than 0, and that's going to be included in our domain. So here, our domain is just x is greater than 0. And if we want to write this in interval notation, we just say, hey, we're going to start at 0 but not include it because we don't have a little line under our inequality sign. We're going to start at 0 and we're going to go all the way to infinity. That's what it means by strictly greater than 0. So this guy is our domain, and our range is going to be negative infinity to positive infinity. Now let's go ahead and sketch the exponential and the log function. So the first thing, we have x, and then we have log base 3 of x. Then we have our exponential, which is x, 3 to the x. So some good points for our log function is, let me write this down here. Some good points for log function. Some nice points. When the argument is 0, that is the vertical asymptote. So that's one important point here. So let's do that first. So when x is equal to 0, well, okay, so x is equal to 0. That's where our asymptote is undefined. And the next good point is when the argument equals 1. So this was our first good point. Our second good point is when the argument equals 1. So when x equals 1 in this case, so that's x is equal to 1, what's our output going to be here? If we have log base 3 of 1, well, remember what this is saying. This is the base. This is saying 3 to what is equal to 1? Well, and that's our output, our y. That has to be 0, right? So one of our points here is going to be 1, 0. So since we have an inverse function, 3 to the x, we can switch the 1, 0 to 0, 1 for a point on there. And then maybe we can do, if when x is equal to 1, if I plug 1 in there, I get 3 to the first is just 3. So there's some points there. So let's go ahead and just do a quick rough sketch of these graphs. So our sketch, well, we have our vertical asymptote for this log, and then we have 1, 0 for the log. So it's going to look something like this. It's going to hug that vertical asymptote, and it's going to be increasing. So that is our log function right here. And then our exponential function, well, we have the points x equals 0, y equals 1, so maybe right here. X equals 1, y equals 3, so maybe like that. And then we just connect the dots. And remember, this thing is going to hug the horizontal asymptote, which is 0, right? So it's going to go something like that. This thing is never going to reach 0. And we can see from my my poorly drawn picture that we have mirror images of each other across the line y equals x. So that's a little rough sketch of our picture here. Notice that the horizontal asymptote of the exponent is the vertical asymptote of the log, both 0, right? This guy is going to be y equals 0. That's the horizontal asymptote for the 3 to the x. And this green guy is going to be x equals 0. That's the vertical asymptote of the log function. All right? So let's do another example. We're going to do plenty of examples, and hopefully you guys can get the hang of it. Well, again, we have this form, y equals b to the x, and y equals log base b to the x are inverses, right? And so here our b is our e, because that's our base. And so that means the inverse function, is going to be y equals log base e of x, which we know log base e is the same thing as ln of x, right? So that's our inverse function, y equals ln of x. And it's asking us to find the domain, range, and to find the vertical asymptote and to do a quick little sketch. Okay, so the domain here for our log function, remember it's going to be everything in the argument bigger than 0. So x is bigger than 0, right? And in interval notation, that's going to be we start at 0, but we don't include it, and we go all the way to infinity. So this is our domain here. Now the range, because this is just a basic log function, the range is always going to be negative infinity to infinity with these basic log functions. And let's talk about the vertical asymptote. I'm going to denote that as VA. So that is where the argument is going to equal 0. So the argument here is x. When does x equal 0? Well, at x equals 0. So this is our vertical asymptote. We've got our domain, range, vertical asymptote. And let's do a quick sketch of both of these guys. So with the exponential function, or actually let's do the log first. So again, the vertical asymptote is at x equals 0. So that's that green dashed line. And then, to get another point on this thing, remember we like the asymptote. So let me do a little t-chart here. We have x and we have ln of x. And we already took care of the asymptote. When x is 0, the output is undefined. We also want to see what happens when the argument, in this case, is just x is equal to 1. So when we plug in 1 in here, what is ln of 1? What is ln of 1? Well, if you look at your calculator, it's going to tell you 0, right? Or you can think of it as log base e of 1, and you can think to yourself, e to what power equals 1? That has to be 0. So that's our output here. All right, so 1 comma 0, and so our log function is going to hug that vertical asymptote, and it's going to be increasing forever and ever like that. It might be good to find another point here. If we plug in, for instance, x equals 2, we get the ln of 2, and let's see what that is in our calculator. ln 2, we get about 0.69. So this guy is going to be about 0.69. That might be a little bit closer to the x-axis, but that's okay. So maybe I'll actually write this as an ordered pair. This is 2 comma 0.69. This guy is 1 comma 0. All right. And for our exponential function, we have x, and we have e to the x. So again, we can just kind of flip these values here. When x is equal to 0, y is equal to 1. So flip these values mean these values right here. When x is equal to 0.69, when x is equal to, when x is equal to 0.69, y equals 2. So we're flipping the values to get some points for our inverse function. And we know that our horizontal asymptote is also going to be 0. So it's going to be this dotted line right here. So this is going to be y equals 0. And then if I plot the points 0, 1, that's this guy. This is 0, 1. And then we have 0.69, 2. So that's going to maybe be like this. And so this thing is going to get very close to y equals 0, but never actually touching it. So this is the point, 0.69, 2. So there are our functions in green. We have our log function. So we have y equals ln of x. And in black, we have our exponential function, which is y equals e to the x. And notice the relationship between domain and range here. Now this is the domain, range, and asymptote of the log. So everything's flipped for the exponential, which means the domain of the exponential is -infinity to infinity. The range of the exponential is 0 to infinity, and we can see that, right? The lowest y value this thing goes is 0, but not including it, and the highest it goes, well, it goes up forever and ever. So cool little relationship there with inverse functions. Okay, so I want to kind of, no pun intended, but shift gears a little bit. We're going to talk about transformations, and in particular, we're going to look at horizontal shifts and vertical shifts. But before we talk about that, we need to talk about what a parent function is. So in the simplest way possible, a parent function has no transformations. It's just a plain old vanilla function with no shifts, stretches, shrinks, nothing like that. So for example, we have just a basic exponential function with a base 2 raised to the x. So this is just very boring function. Another exponential here, another log. We also can look at functions, quadratic functions, x squared, just a boring function with its vertex at the origin. We have the absolute value of x. We have x cubed. These are all just regular functions that haven't, we're not adding any numbers to them. We're not subtracting any numbers. We're not multiplying any numbers by them. So that is the idea here. Okay, so the first thing I want to talk about is what's known as a vertical shift. And basically what you do is you add or subtract a number to a function to move it up or down. So that's a vertical shift. So with our exponential functions, we can add a number that I'm calling v, and it's going to move it up v units. We could also subtract a number v and move it down v units. Same thing with the logarithm. We can really do this to any parent function. So any of the functions on this list, you can add or subtract a number, and it's going to either move it up or down depending if you add or subtract. Okay, so the vertical shift is also going to move the exponential's asymptote, but it's not going to do anything to the log's asymptote. So let's just look at some examples here of vertical shifts. So here I have the function y equals 2 to the x plus 3, and you can see it in this graph right here. It's in green. So what would our parent function be? Well, our parent function would be just this boring function y equals 2 to the x, which is in red right here. And this number at the end is telling us how much I need to shift the parent function up. And we can see that we're shifting it up 3 units. So every point on the parent function gets moved up by 3 units, each y value. Okay, so what is the domain of this transform function? Let's think about that. So what is the domain of this green function that we can see here? Well, the domain is going to start at that, and maybe I should do this in yellow to be consistent with the horizontal asymptote. Let's just do this real quick. So the horizontal asymptote is going to be at what? Well, originally it's at y equals 0, right? So this is just a boring function. The horizontal asymptote is always at y equals 0 with no transformations. But I'm going to move it up 3 units because I'm shifting the whole function up 3 units. So the new horizontal asymptote is at y equals 3. All right. So what's the domain and the range? Well, the domain doesn't change. The domain is basically, hey, what can I put in here for x? What can my x values be? Or if you want to look at it graphically, you can say how far to the left does this green curve go to how far to the right does it go? And it goes on forever and ever. So the domain here is going to be negative infinity to positive infinity. Now the range, on the other hand, the range of the parent function, the boring function, well, that starts at the horizontal asymptote, which is 0, and it goes all the way up to infinity. With the shifted function, this time the range is starting at the horizontal asymptote again, which is 3 this time, and then it's going to infinity. So we're shifting it up. So this time we're going from 3 to infinity, and it makes sense that the range would be affected here because we're moving it up and down, right? We're shifting the function up and down. So that is our first example looking at the domain, range, and asymptote of a shifted up function. Let's do an example with logs. Okay, so first of all, let's look at this picture and figure out what the asymptote is. So the asymptote, we can see, well, it's always going to be the where the argument is equal to 0. So this is just going to simply be at x equals 0, right? And we can see that on the graph. We can see that both of these functions are hugging x equals 0. So that's my asymptote. Now my range, again, even though it's shifted, it's still negative infinity to positive infinity. What's the domain? How far does it go to the left to how far does it go to the right? Well, it doesn't go past the asymptote. It doesn't go past x equals 0. So we're going to start at x equals 0 but not including it. And we're going to go all the way to the right out to infinity. So that is our answer there. Okay, let's talk about horizontal shifts. So horizontal shifts move a parent function to the left or to the right. Now, it's opposite of what you think with horizontal shifts. With vertical shift, it's pretty straightforward. You see a plus sign, we're moving it up. You see a negative sign, we're moving it down. But for horizontal shifts, it's the opposite. When you see a negative sign, we're actually moving to the right. Okay, so it's opposite of what you might think. It's going to shift the graph to the right. And so we can see it in the exponential form like this, x minus h, where h is a number. It's moving it h units to the right. We can also see it with a log graph. This is taking the basic log base b of x. It's taking it and it's picking it up and moving it h units to the right. On the other hand, if you see a plus sign, we're moving to the left. So again, it's opposite of what you think, and if you just keep that in your head, you should do fine with this. But just remember that x plus h, we're taking the graph and we're moving it to the left, h units. Okay? So another thing is that since the since we have this basic log function and it looks something like this, if we're shifting this thing over, it's going to take the asymptote with it. Okay, if we're shifting it to the left or the right, the asymptote comes with it. So let's do some examples with that. Okay, here is our first example. We have y equals 2 to the x minus 1. We want to figure out what is the domain, range, and asymptote. So this is just an exponential function. Let's actually write a little thing down here for transformations. Maybe I'll spell it out for now. So transformations. So since this minus 1 is in the argument where the x is, it's shifting it horizontally. So this is being shifted horizontally to the right 1 unit. Okay, so this green is y equals 2 to the x minus 1, and the red is just going to be y equals 2 to the x, which is the parent function. So we're moving the parent function to the right 1 unit. Okay, so what's the domain? Well, the domain doesn't change with the horizontal shift here, right? Because we can see that we can plug in any x we want and we'll get a valid input. We only have problems with the domain when we have variables in the denominator and variables under square roots. So no problem here. We still have a domain of negative infinity to positive infinity. Our range is going to start at the horizontal asymptote, and when we shift it left and right, when we shift this exponential left and right, that horizontal asymptote is not going anywhere, right? It's still staying at y equals 0. So the range is going to be starting from y equals 0 all the way to infinity, okay? The asymptote is still at y equals 0. We didn't move the function up and down, so the horizontal asymptote stayed where it is, okay? So that is our first example there. Let's look at a log function. So the domain is going to change because we're shifting it. We can see that the argument, x plus 1, is a shifted version of just x. So I'm going to add a little thing down here for transformations. And so there's no vertical shift. There's a horizontal shift because the plus 1 takes place inside the argument with the x. So this is going to be a horizontal shift to the, well, it's opposite what you think with horizontal. So it's going to be to the left 1 unit. And we can see that in our picture here. This red guy is just our boring parent function. I shouldn't say boring. Maybe I should say simple. I don't know if that's better. Well, this is our simple parent function, log base 2 of x. This green guy right here is our shifted function, y equals log base 2 of x plus 1. So we're shifting that parent function. We're literally picking it up and moving it to the left 1 unit to get this new function. So what's the new domain of the green guy? Well, we have to first consider what the asymptote is. The asymptote happens when this argument is equal to 0. Solving for x, we get that the horizontal asymptote is at x equals negative 1. So let me just do a dot right here. So sorry, I think I said horizontal, I meant vertical asymptote. This vertical asymptote is at x equals negative 1, and therefore that's where our domain starts. We're starting at negative 1, right? The asymptote shifted to the left when we shifted the whole function to the left. It was originally at x equals 0 for the red guy. We moved it over to the left 1 unit, so now that asymptote is at x equals -1. So the domain is going to be starting at -1 and all x values out into infinity. As we can see with the curve here, it's going to go all the way out to x equals infinity. The range, again, is pretty basic here. It's just all real numbers, -infinity to positive infinity. Because again, with these shifted log functions, we don't have to worry about the range doing anything. It's still going to be all real numbers. Okay, so that was our log example there. All right, so let's practice identifying which function belongs to which equation. So we could have combinations of vertical and horizontal shifts, and the function that I'm shifting right here is just the basic parent function y equals x squared. And we can see that the basic parent function on this picture is going to be the red guy because the origin is the vertex, and it matches up with all of the points on y equals x squared. It's not, so the vertex, that's the key thing. If the vertex is at 0, 0, and all we're dealing with are shifts, then you know that that has to be the parent function. What about the next one? We have shifted to the right 2 and up 3. So horizontal shift to the right 2, opposite of what you think, up 3, same as what you think. And so from the parent function, it looks like the only one that could possibly be moving the vertex to the right and up is this one. I'm just looking at what's happening to the vertex. Well, the green guy, I'm moving it to the right and up. And that's the other ones here, I'm not moving to the right at all. So it has to be the green guy. Okay. All right, what about number 3? We are moving to the left 4, indicated by the +4 in the argument, and then we're moving down 5. So left 4, down 5. So if we start at the vertex here, the only one that's moving the vertex to the left is this purple guy. We're moving it to the left and then down, whereas the blue one, we're just moving it down. So it has to be the purple guy here. And finally, the blue one has to be x squared minus 9. Now we're not shifting it horizontally, we're only moving it vertically, right? Because the argument is x minus 0. We're not moving it horizontally at all. So this is just down 9 units. And we can see that right here. We are moving the parent function's vertex down 9 units to get this new transform vertex. All right, so let's do some examples here with combinations of vertical and horizontal shifts. First of all, I want to point out what the transformations are. So what's our parent function here? What's our boring function? Well, no shifts in the argument and no vertical shift. So it's just going to be y equals 2 to the x is our parent function. And if we look in our argument, what's happening to the x? Well, +1, which means we're moving not to the right. It's opposite what you think. We're moving to the left 1 unit. So the transformations here, we're going left 1 unit. And then this guy, this -4 after the function, is telling us we're shifting down 4 units. Those are our transformations. We might want to do a sketch first before we look at the domain and the range. Let's do just a quick little sketch here. Well, and I'll just do like a little baby t-chart over here. So we have 2 to the x plus 1 minus 4. Okay, so when x is equal to 0, we have 2 to the 0 plus 1 minus 4, which is minus 2. So 0 minus 2. We also know where our horizontal asymptote is based on the vertical shift. The horizontal asymptote is going to be at our vertical shift, so it's going to be at -4. So let's just do a quick little sketch of that. So this is our horizontal asymptote, y equals -4. And maybe we can do one more point. How about we do x equals 1? When x equals 1, we have 2 squared minus 4, which is just 0. So that is going to be our y-intercept here. All right. So this is an increasing function, right? It's an exponential function. And so it's going to look kind of like this. All right, so that's the graph of our function. It's going to get really close to that horizontal asymptote, but it's never going to touch it. So domain and range. Well, domain's not affected here, just like the range isn't affected with the logs when you shift it. So the domain here is going to be all real numbers, -infinity to +infinity, just like it always is. We have no restrictions for what we can put into the argument here. The range, on the other hand, what's the lowest y value this thing will obtain? Well, it's going to hug that horizontal asymptote forever. It's never going to touch it, but it's going to get arbitrarily close to it. So the range is starting at y equals -4, and we can see that this thing grows forever and ever and ever. So it's going to grow to infinity. Okay, and we did our sketch up here. So this is our sketch. All right. Let's do another example. This time we have a logarithmic function. So let's talk about the transformations first. What's our boring parent function? Well, our boring parent function doesn't have any shifts in the argument, and it doesn't have any shifts after the fact, after the function. So the parent is simply y equals log base 2 of x. Okay, so the transformations here, well, we can see inside the argument -3. Inside the argument is opposite what you think. We're going to be shifting to the right 3 units. We also have a +1 after that. So that's telling us we're going to move this thing up 1 unit. Okay. So let's talk about the sketch of our graph next. So first thing, I'm going to make a pretty simple t-chart here. Remember the 2 points we really care about with these logarithm functions? We care about the vertical asymptote, and we care about when the argument equals 1. Those are some pretty nice points to deal with. So first of all, for the asymptote, we have to set the argument, which is x minus 3, equal to 0 and solve for x. So the asymptote occurs for the x value that makes the argument 0. Okay? So adding 3 to both sides, we see that the asymptote is x equals 3. So that is our asymptote here. So when x equals 3, it's undefined. That's where our asymptote is. And the next value is, the next nice x value happens when the argument equals 1. So when the argument equals 1, we add 3 to both sides to get x equals 4. So that's our next nice x value. All right, so let's put that here. When x equals 4, what is our output? Well, we have log base 2 of 4 minus 3 plus 1. So we have log base 2 of 1 plus 1. This guy, 2 to what power equals 1? That has to be 0, right? 0 plus 1 at the end equals 1. So our output is going to be 1. I think I did that right? So let's see. Yeah. Our output is going to be 1. Let's double check my math here. I think that's right. Yeah. Okay, good. All right. So input is 4, output is 1. We could add another point in here if we really wanted to. What could I do? How about the next obvious one, 5? When x is equal to 5, we get log base 2 of 5 minus 3 plus 1. Log base 2 of 2 plus 1. 2 to what power equals 2? Well, that has to be 1. 1 plus 1 is 2. So our output is 2. All right. Now we have some good points here. So using this, let's go ahead and do our sketch down here. First thing, I'm going to plot my asymptote, my vertical asymptote at x equals 3. So here's my vertical asymptote. And then I'll do my points. So when x equals 4, y equals 1. When x equals 5, y equals 2. And so it's going to kind of look like this, hugging that vertical asymptote all the way down. So that's my sketch. And what's the domain and the range going to be? Well, when I shifted it horizontally, I moved the asymptote. The asymptote of the parent function is simply at x equals 0. But since I shifted it to the right 3 units, the asymptote is now at x equals 3. And therefore, the domain is, we're going to start at x equals 3, but not including it. And then it's going to include all of the x values after that. So our domain is from x equals 3 all the way to infinity. Range is still the same. Negative infinity to positive infinity. How far down to how far up does this thing go? Okay, so let's look at this next example. Now, you should notice something weird about the base in this case. So the base is 1/2, right? And I want to make a little side note over here that you should put in your notes. So when the base is less than 1, we have a decreasing log function. Okay, so the ones that we've looked at so far were all increasing. So like this guy, what do I mean by increasing? Well, I mean as time goes on, aka x-axis, as the x's get bigger, as time goes on, the y's also get bigger. So this is increasing when it looks like that. When the base is less than 1, we're going to have a decreasing function. So we're going to have something that looks like this. Like exponential decay, if you want to think of it like that. So when time goes on, the y values get lower and lower, so this is decreasing. This is a decreasing function. All right, so let's go ahead and look at this thing. So first of all, what are the transformations? Well, if we look inside the argument, what's happening to x is we're adding 1, and so this means it's being shifted to opposite of what you think, to the left 1 unit. And then this -3 after tells me we're shifting down 3 units. That's a vertical shift. All right, so let's first look at what our asymptote is. Our asymptote occurs when this argument is equal to 0. So we have when the argument is equal to 0, we get that our asymptote, maybe I should do this in green, just to be consistent with the colors. Our asymptote is going to be -1 when we solve this. So that's our vertical asymptote. And let's get a little t-chart going so we can get our sketch and then talk about domain and range. So we have x, and then we have log base 1/2 x plus 1 minus 3. So the first key point is the asymptote. When x is equal to -1, this thing is undefined because the argument is going to equal 0. So that's our first big thing. The second nice point that we have is when the argument equals 1. So when the argument equals 1, if we subtract 1 from both sides, x had better be 0, right? So that's our nice point here. When x is equal to 0, we get the following. We get log base 1/2 to the 0 plus 1 is 1 minus 3. Now this thing right here says 1/2 to what power is equal to 1? Well, it has to be 0. Anything raised to the 0 power is 1. So this thing is 0. 0 minus 3 is minus 3. So my output here is minus 3, corresponding to an input of 0. So let's write that here. Let's erase some stuff. So this is going to be minus 3 undefined. And we might as well do one more point here. How about the next point? How about when x is equal to 1? Well, when x is equal to 1, we have log 1/2 of 1 plus 1 minus 3. So this is log base 1/2 of 2 to the minus 3. What is this saying right here? This is saying 1/2 to what power is equal to 2? 1/2 to what power is equal to 2? Well, we could think of this, we could think of 1/2 as 2 to the minus 1, right? If 1/2 is 2 to the minus 1, then we have 2 to the minus 1 question mark is equal to 2 to the first. What does the question mark have to be in order to make this true? It has to be -1, right? Because -1 times -1 is going to give us +1. So our answer here is -1. So this all goes to -1. All right? So -1 minus 3 is going to give us an output, final output of -4. So when x is 1, our output is -4. Let's write it down. Okay, so now that we have some points, let's do our little sketch here and talk about domain and range. So first thing I do is I do a little sketch of my vertical asymptote. In this case, it's x equals -1. Then my next point is 0, -3. And then followed by 1, -4. Okay, so as I said before, since the base is less than 1, it's 1/2, this thing is going to be decreasing, but it's still going to be hugging that vertical asymptote. So our sketch is going to kind of look something like this. It's going to look something like this. So it's decreasing, but it's still hugging the vertical asymptote. Okay, so that's our sketch. Let's talk about domain and range. We can see from the picture, the range, of course, is going to be all real numbers. It's shifted, we don't care. It's still how far down to how far up, -infinity to +infinity. Now our range, our parent function's domain was from 0 to infinity. Here we shifted this thing to the left 1 unit, so our new domain starts at x equals -1 but doesn't include it, and it goes all the way to x equals infinity. So we're going from -1 all the way to infinity. So that is our domain there. All right, let's do some more examples here. I encourage you to pause the video and try this one out for yourself. Transformations. Let's look at that first. Now, what's happening in our argument? That's a shift to the right 1. So shift right 1. And then we have a vertical shift. This is a shift up 2. Cool. All right, let's talk about our asymptote. Our asymptote occurs when the argument equals 0. When the argument equals 0. So when x minus 1 equals 0 and we solve for x, we get that our asymptote is at x equals 1. Okay? All right, let's do a little t-chart so that we can do a sketch. First thing is my asymptote, my first key point here. When x is equal to 1, we have an undefined answer, which is going to be where my vertical asymptote is. The next key point occurs when my argument equals 1. That's another nice point. When does my argument equal 1? What does x have to be? Well, if I add 1 to both sides, x had better be 2 for my argument to equal 1. Argument's what's in parentheses, okay? So when x is equal to 2, what happens here? I get log base 4 of 2 minus 1 plus 2. This becomes log base 4 of 1 plus 2. Now what is this whole thing going to? This is saying 4 to what equals 1? That has to be 0. So this whole thing has to go to 0. 0 plus 2 is 2. So our output is 2. Our input is 2, our output is 2. I'm going to be kind of lazy and just not get another point. This is enough because my base is 4, which means it's increasing. I know it's going to be just a basic sketch. So here, I'm going to do my vertical asymptote first at x equals 1. Can't touch this. And then my next point is at 2, 2. So maybe like right here. And it's increasing because the base is 4, which is bigger than 1. So it's going to be increasing as time goes on, the y values increase. And it's going to be hugging this this vertical asymptote. So there's a rough sketch right there. What's the domain and the range? Well, the range, pretty boring, just all real numbers again. How far down to how far up? Again, it's always going to be all real numbers with these shifts. So if you have a parent function, if you have a log parent function, range is all real numbers. If you have shifts of that parent function, range is all real numbers. We may talk about some special cases next week, but for now, range is all real numbers. And we can see it from the graph, and we can think about it in the equation sense. Now, I do want to warn you, if you put this in Desmos, it's not going to look like the range is all real numbers, okay? Because, I don't know, it does a weird thing where it cuts off at the asymptote, but just know that Desmos is not pictorially accurate in that way for these logarithms, okay? So range is all real numbers. What's the domain? Well, the domain of the parent function is going to be everything bigger than 0. Since we shifted this thing to the right 1 unit, the domain is now going to be 1 to infinity, all right? So what are our x values? Well, x starts at 1, but not including 1 because that's where the asymptote is, and it goes all the way to x equals infinity. All right, let's do a kind of strange example here. So it's not really obvious what the transformations are because we're not in that specific form where we have an argument and we're adding and subtracting just a number, and then we have a vertical shift on the outside. So we're not really going to get into transformations here. But I do want to talk about domain and range, okay? So the first thing that we need to look out for is what values of this argument is going to make the argument 0, right? So we're interested when is x squared minus x minus 20 equal to 0? Well, this is a quadratic, right? It's of the form ax squared plus bx plus c. And we know how to deal with quadratics. We factor them, right? Or if we can't factor, we use the quadratic formula. But this looks like a good quadratic to factor. It has 3 terms. I'm looking at c, in this case, is negative 20. And I'm saying what 2 numbers multiply to negative 20 yet add to negative 1, right? That's how we factor things. So let me write this down. So what 2 numbers add to negative 20? Or sorry, what 2 numbers multiply to negative 20 yet add to negative 1? What are those 2 numbers going to be? Well, that's going to be negative 5 and positive 4. All right, you multiply negative 5 and positive 4, you get negative 20. You add negative 5 plus 4, you get negative 1. Perfect. So this thing factors in the following way. We have x minus 5, x plus 4 equals 0. And we want to be careful here because when we set these factors equal to 0, we're going to get key points that we need to test, okay? Because when you're dealing with quadratics, some weird things go on and you get extraneous solutions. So we want to just test these points starting out. So what we get when we set each of these equal to 0 is we get x equals 5 and x equals negative 4. And what I'm going to do is I'm going to put these things on a number line. I'm going to put these things on a number line, and they're going to act like my test points. So here's negative 4, here's 5. What I want to do is I want to see when the argument is greater than 0, right? Because if it's greater than 0, I can include it in the domain. If it's 0 or less than 0, I need to exclude it. So the question is, what's happening with the numbers less than negative 4? What's happening with the numbers less? Well, what if I pick a test point of negative 5? So this is my test point. If I pick a test point of negative 5, well, I can put negative 5 in here and see what happens. So I have negative 5 minus 5 times negative 5 plus 4. Is that less than 0? Well, no, because I have negative 25 times negative 1, which is positive 25. So 25 is greater than 0, right? So what this is saying is that from negative infinity all the way to negative 4, I have values greater than 0. So I can include this in my domain. All right? What about between negative 4 and negative 5? How about I pick 0 as a test point? If I pick 0 as a test point and I plug that into these values here, I get 0 minus 5 times 0 plus 4. And how does that compare to 0? Well, I get negative 5 times a positive 4, which is negative. And that's going to be less than 0. So from negative 4 to 5, I'm getting numbers that are less than 0. let's pick a test point after 5. So after 5, how about I pick the test point 6? Well, let's plug in 6 for x. We get 6 minus 5 times 6 plus 4. What's that in relation to 0? Well, we get 1 times 10, which is greater than 0. So these are all greater than 0, indicated by the positive numbers. Okay, so what this is telling us is I can include this in our domain and this in our domain, but I cannot include anything between -4 and 5 because those values are going to give us an argument that's less than 0. All right? So, first of all, what are my asymptotes? My asymptotes occur at -4 and 5, right? Because those are the values that make the argument 0. So we have x equals 5 and x equals -4. The range is still -infinity to positive infinity. And the domain is going to be, well, where on our interval it's positive. We're positive from -infinity all the way up to -4, but not including it. And we're going to union that with this side. So this side is going to be from 5 to positive infinity. And what's the graph going to look like? I'm just going to do a very rough sketch of what the graph would look like. If you put it in Desmos, you can see a better picture. But okay, so here we have our horizontal asymptote, x equals -4. We have another one over here at x equals 5. And then everything to the left of -4 is going to be in our domain, so we have a nice little picture here for that. And then everything to the right of 5 is going to be in our domain, so we have a nice little picture here. But notice that between -4 and 5, we don't have a picture because those are values that make our argument negative. All right, so that's the idea for that example. Okay, so let's talk about finding inverse functions algebraically. Do you remember what we did a few sections ago? We swapped the x and the y values, and then we solved for y to find the inverse function. So that's what we're going to do here. So here we have a function y equals 2 to the x. To find the inverse, we're just going to swap x and y and solve for y. This is something we've talked about before. So we have x equals 2 to the y, right? Now, how do I figure out what y is? Well, one natural way to do this is to take the log base 2 of both sides to cancel out the base 2. Remember, that was our inverse property of logs and exponents that we talked about last week. Or maybe it was the week before, I can't remember. But anyway, we're going to take the log base 2 of both sides. Now, could you take the ln of both sides and still get a valid answer? Yes. Yes, you would. I'm not going to go into why that is, but it would be something good to think about. So, but I'm just going to do log base 2 because it's the most natural thing to do here. At least I think it is. Now, because of that inverse property that we talked about either last week or the week before, that guy's going to cancel on the right, and we're simply going to be left with y equals log base 2 of x. So we have found our inverse function algebraically. Okay, so now it's time to talk about the domain and the range of both functions. So our first function is y equals 2 to the x, the domain, and the range. What else does it say? Okay, that's it. Then we have our inverse function, log base 2 of x, domain, range. Well, if we look at our possible inputs into the argument, remember, the argument can't be less than 0 or equal to 0. It can be anything larger than 0. So the domain is just our regular, we're starting at 0 and we're going off to infinity. The range is all real numbers. And because we have inverse functions, the domain and the range are going to swap. So the domain of the exponential is the range of the log. So the domain here is negative infinity to positive infinity. And the range is the domain here. So it's going to be from 0 to infinity. And what I'm going to ask you to do is you should verify this for yourself on Desmos. You should check out Desmos and make sure that these all match up. All right? All right, cool. So here's a picture on Desmos. Now, it's pretty clear from the picture that if we have the line y equals x, that's our magic reflection line with inverse functions, it's pretty clear that the points are mirror images of each other when you look through the mirror y equals x. Okay, so it's pretty much like a folded over version of one another. Now, remember how we proved that two functions were inverses? Remember how we did that? Well, we had to show two things. We had to show that f inverse of x was equal to x, and we had to show that f inverse of f of x equals x. We had to show those two things. Now, in this case, we said, it doesn't really matter, but we said that the exponential function was f. That was our starting function. And then we said that this log function was our f inverse. So let's check the first condition. So let's check 1. And to do that, we're putting the inverse function inside of f. So we're putting log of 2 of x inside the x for f. So we have 2 instead of x, we're putting in log base 2 of x. Okay. And remember the inverse property that we talked about, we have base 2, log of 2 cancels out, and we're simply left with x. So that checks out. Let's verify condition 2. So this time we are plugging in f into the inverse function. So in this guy right here, we're putting in 2 to the x. All right? So we have log base 2 of 2 to the x. Well, indeed, log base 2 of 2 by that inverse property, and this might be a little circular logic-y, but I just want to show you guys that this works, is what I'm trying to show you here. So the log base 2 and the 2 are going to undo each other, and we're just left with x here. So since the first and the second condition are met, they are inverse. Oops. They are inverse functions. Okay. Let's look at another example. So this one's a little bit more involved. It looks like we have an exponential with a horizontal shift to the right 1 unit and a vertical shift up 4 units. So we're going to do the same thing that we do. We're going to swap the x's and the y's, and it tells us state the domain and range of both functions. So if we swap the x and the y, we have x equals 3 to the y minus 1 plus 4. So we want to get y by itself. So the first thing I'm going to do is I'm going to isolate the exponent term, and I'm going to subtract 4 from both sides to do that. So x minus 4 equals 3 to the y minus 1. Now to undo the base 3, what I can do is I can take the log base 3 of both sides. And again, you can take the ln of both sides, and you're going to get an equivalent inverse function. But just for simplicity's sake, I'm going to do it like this. All right? So I did that so that these cancel out. And on the left, I'm left with log base 3 of x minus 4. And on the right, I'm just left with y minus 1. Adding 1 to both sides, I get y is equal to log base 3 of x minus 4 plus 1. So this is my inverse function. So this is f inverse. And f is equal to, well, what we started with, 3 to the x minus 1 plus 4. So these two guys are inverse functions, inverses of each other. All right, so let's look at the domain of this log and the range. Well, we know what the range is going to be. It's just a shifted log function, so it's going to be negative infinity to infinity. The domain, on the other hand, starts at when the argument equals 0. That happens when x is 4. So we're starting when x equals 4, and we're going off to infinity. So with the exponential, remember, since they're inverses, the domain and the ranges switch. So the domain here is the range of the log. So the domain is just all real numbers, negative infinity to positive infinity. And the range, we can see that we're shifting this thing up 4 units. So the range is going to be, well, the domain here, 4 to infinity. All right. So here's our functions. We can see that they are indeed reflected across the line y equals x. It's the mirror for them. And let's prove that they're inverses. So remember, this was that our f? Yeah. So this was our f. This was our f inverse. So the first condition was that f inverse of x equals x. So our first condition is that f inverse of x equals x, and our second condition was that f inverse of f of x equals x. So let's check the first one. So the first one, we're plugging in f inverse into the x value of f. All right? So we're doing 3 to the all of this f inverse log base 3 of x minus 4 plus 1, all of this. And then we still have that minus 1 at the top plus 4. Okay, so that's f of f inverse. We're plugging in f inverse into the x in f. All right, so that guy cancels that, and we're just left with x minus 4 plus 1 minus 1 plus 4. Minus 4 plus 4, 1 minus 1, well, that just equals x. So that first condition is met. For the second condition, we're plugging in f into the x value of the inverse function. So we're plugging the whole function of f into this x right here. So this is going to be log base 3 of 3 to the x minus 1 plus 4. We still have minus 4 plus 1, okay? All right, so by the inverse property, those cancel. I'm left with x minus 1 plus 4 minus 4 plus 1, and 4 minus 4, negative 1 plus 1. This just equals x. So indeed, the second condition is met, and therefore, since both conditions are met, they are inverse functions. All right, let's do another example. I encourage you to pause the video at this point and try this one out for yourself. Okay, this time we have a log function. We want to find the inverse. So we swap the x's and y's first and solve for y. So we have x equals log base 5 of y minus 8 plus 1. Let's isolate the log term by subtracting 1 from both sides. Now, how do I undo a log base 5? Well, I can take 5 and raise it to the log base 5, right? So I'm going to take 5 as the base, in both the left and the right side. So I have 5 to the x minus 1, 5 to the log base 5 of y minus 8. That way on the right, those guys cancel, and I'm left with 5 to the x minus 1 is equal to y minus 8. Finally, I can add 8 to both sides to get my inverse function. Y is equal to 5 to the x minus 1 plus 8. So this is our inverse function. Okay, so let's find the domain and the range. So the first thing is we started with log base 5 of x minus 8 plus 1. And then our inverse was 5 to the x minus 1 plus 8. All right, so what is my domain and my range for this log? Well, the range is easy. It's negative infinity to positive infinity. We know that. The domain starts when the argument equals 0. So when does the argument equal 0? When x equals 8. So the domain, we're starting at 8. We're going to infinity here. Switching the domain and the range for the exponential. This time the domain is the range of the log. The domain of the exponential is the range of the log, so it's going to be negative infinity to infinity. And the range is going to be 8 to infinity. We're just switching out the domains and the ranges here. All right. Proof that they are inverses. Let's try this out. So here's our graphs as seen here. Going through the line y equals x. We have these mirror images of each other. And now we want to prove those conditions. So condition 1. Okay, so we want to prove these two. So for condition 1, we're putting in f inverse. So, okay, so actually we started with this as our regular function. So this is f. Again, it doesn't really matter which one you call f and which one you call f inverse, but just be consistent. So we're plugging in 5 to the x minus 1 plus 8 into x for f, okay? So let's go ahead and do that. F of f inverse is going to be log base 5, and instead of x, we're punching in f inverse, 5 to the x minus 1 plus 8, and then we still have that minus 8 plus 1. Log base 5 and 5 cancel. We have x minus 1 plus 8 minus 8 plus 1, and of course that all goes to 0 to just leave us with x, so that first condition is met. Let's do our second condition. We're plugging in f into the inverse function for x. So we have 5 to the log base 5 of x minus 8 plus 1 minus 1. So this whole thing is our input, plus 8 on the outside. The 5 log base 5 are going to cancel, and we're left with x minus 8 plus 1 minus 1 plus 8, and that all goes to x. So the second condition is met, therefore the functions are inverses. Okay, it appears that we're at the end of the lecture. I hope you guys learned something. Thanks for watching, and I'll see you guys next time.